Well, hello everyone. Welcome back. In this video, I want to address a previous video that I had made, particularly the lux readings of the sun points to a globe Earth. And I want to clarify one thing. I think the title is misleading. I'm probably going to put a question mark here and update the description. Pretty much everything that I said in that video, I still stand by it. Watch this video for all the details I explained it in there. So the point of this video is to clarify a couple of points. The first is that from my subsequent observations of lux readings, the answer, can you use lux readings of the sun to point to the shape of the earth? I would have to say that the answer is no. The lux readings, unfortunately, cannot be proven one way or the other, and I'm going to get into that in this video. The other thing that I want to address is that the app that I was using for the phone, as I described in this video, doesn't really work very well. So those are the two main points that I wanted to bring up concerning these two videos. So this video still stands. I'm going to update the title with putting a question mark here and update the description in this one to point to the new video that I'm making now. The problem that I had with the app that I was using to measure the lux readings through the tissue paper did seem to give a reasonably accurate correlation to what I'm about to explain a little bit further. But the readings I got through the copy paper and reflected off the copy paper were so far out of each other that I didn't want to trust any of them. So as far as I'm concerned, lux readings from the phone, from the app on the phone, not particularly well suited. I'm just going to have to toss all of that out, unfortunately, although it was a good learning experience. So now on to the topic of this video. As I stated in this video here, the possible lux readings issues in my previous video, I did state that I was going to consider using a different form of light metering, and I did hint at the possibility of using a photoresistor, and that's exactly what I did. I went into one of my Arduino hobby kits and I borrowed the photoresistor that came from it, and I just used a multimeter in the ohms setting to measure the resistance of the photoresistor. In direct sunlight, it was getting pretty close to the tens of ohms. I used a piece of copy paper as a direct line of sight shield to attenuate the sun's intensity and also to diffuse it, to increase the field of view of where the light is coming from. So at this point, I'm going to inject one of the other videos that I made earlier that shows the construction of my light meter and how I ended up using it. So I've got in my hand here a multimeter set in ohms scale. Over here you can kind of see this little red spot right there. That's a photoresistor, and I've got that hidden behind a piece of paper. So we just rotate ourselves this way to find the correct, the lowest spot, right about 329. Then we start angling up and down. So that's 326 ohms. So now that I've got a device that's able to measure the light's intensity in a different way other than the app on the phone, let's look at the results. And I found that in just 2 days alone, the results were much more consistent and much more reliable as far as I'm concerned. Having said that, I can see that the overall trend of the light intensity, which happens to be measured in resistance of the photoresistor in ohms, matches the overall curve of the lux readings from earlier through the tissue paper. So at least there's that much, but unlike the lux readings, and this part is probably due to me rounding it down to the nearest thousand. One thing that I noticed with the photoresistor is that it's not a flat line. There is still a bit of a taper. So the initial slope from sunrise to about 9 o'clock in the morning is a very sharp and steep line, and then it hockey sticks, and then it flatlines. It mostly flatlines, and as you can see, it slowly and gradually reduces in resistance until it reaches local solar noon, and then it'll increase again in resistance gently until it reaches that hockey stick curve, and then it shoots right back up again at dusk. When I saw how this curve looked in just 2 days worth of readings, I felt that I had confidence in the results. So now I could use this to compare against other factors. So I was able to step back and ask myself, what effect does the distance of the atmosphere that the light has to travel through have on the intensity of the light? Is there any correlation that can be drawn between the two? And so then what I did was I created a spreadsheet that I just copied the spreadsheet from my flat earth solar position calculator, which I made a video of earlier. So I just took that spreadsheet, I copied it to this one, and the only thing I had to do was get rid of this last column and replace it with this one, which is the distance in kilometers between the observer and the sun for a specific geocoordinate, a specific time of the year, in a specific time zone, and the atmospheric height, and it generates the solar position as it should be if the Earth was flat. But the thing to consider is that you can see the general shape of the graph. I was more interested in the profile of the curve than I was in the actual units themselves. So then I did something similar for a globe Earth. I didn't want to get too involved in the math, so I simplified the equation and approximated it this way. You look towards the horizon through the atmosphere. Eventually the Earth will dip away from you, but if you keep looking at the horizon, eventually you will be looking past the boundary between the atmosphere and outer space. That's the distance I was trying to calculate. So the way I did that was I used the arcsine function. I knew that the opposite side would be the radius of the Earth. If you think of this as a rectangle, then the opposite side would be the radius of the Earth. The hypotenuse would be the radius of the Earth plus the thickness of the atmosphere. That gave me this angle here, 68.425 degrees. So now I've got the angle. The next thing that I needed to do was calculate the base. And again, this is still the same rectangle, and now I need to calculate the base. So now I use the cosine function of this angle that I just computed, multiply the hypotenuse to give me the base, 2,519 kilometers. And at this point, this is where I simplify the model slightly, because where you are you're going to be looking up towards the sun, and the sun will be at a specific altitude for that given time of the day based on your latitude. And just to keep it as a simple formula, I'm looking to calculate the XY coordinate of the boundary between the atmosphere and space. So what I did was I calculated the X component by using the altitude of the sun with the cosine of this 2519 kilometers, which should ultimately form a circle like this. And then to calculate the Y component, I used the sine of the same altitude of the sun multiplied by the thickness of the atmosphere to create a smaller circle like this. And between these two, it should create an oval that looks kind of similar to the circle of the atmosphere. So that was the shortcut that I took in this particular graph, and it created a curve that looks similar to this. Unfortunately, both the globe Earth model and the flat Earth model provides a similar curve of the distance that the light would have to travel through the atmosphere for that particular time of the day. And unfortunately, I'm not able to correlate either of these to the sun's intensity. So that is why I'm going to have to put that question mark here. Now, I did state near the very beginning of this one, by quoting some websites, which are actually linked in here, I believe. If not, I will put them in here, that the two main factors that affect the sun's intensity are atmospheric absorption and by atmospheric scattering. What would be interesting to find out is which of those two factors deal with each of these slopes. And my guess is that this slope from 9 o'clock in the morning, for example, to local solar noon, that gentle slope is probably caused by atmospheric absorption. I would almost guess that the other slope from sunrise to about 9 o'clock in the morning is probably caused by atmospheric refraction. The reason I say that is at dawn and at dusk, the sky is reddish because the blue light has to travel through so much more air that the blue light gets scattered. So at some point, it's kind of like, you can almost think of it as the reflection versus the refraction of light in an aquarium, for example, where it reaches that particular threshold and suddenly the blue light is now able to get directly to you as opposed to being scattered, rather than get scattered in the atmosphere. So that's the way I interpret these particular slopes. And of course, one of the next things that I can try to do is to prove or disprove these theories. In essence, this is the follow-up to the video that I was making earlier on lux readings. And that's pretty much all I have at the moment on this subject. So once again, if you've made it this far, thank you for watching the video. Don't forget to like, subscribe, hit the bell to be notified, all of that other good stuff. And hopefully I'll see you again soon in another video. Bye for now.